Hello. So, because I started solving this example in my previous video. So just to remind you, we have this extended robotic arm, and this point B extends. This length, the small l, increases at a constant rate, and simultaneously it also rotates about j hat and k hat. We had omega 2 about j hat and omega 3 about k hat. We also know that L is 6 meters at this instant of time, which we are interested in computing velocity and acceleration for. At the end, we are interested in computing velocity and accelerations of point B. We started by defining a body attached frame, and the body attached frame was attached to this robotic arm. And then for this body attached frame, we defined the B1 hat axis, the unit vector for our first axis, to be along the arm. Then we define B2 hat perpendicular to B1 hat and use right hand rule to define B3 hat, which is along K hat. Then we started by computing velocity in this frame. So R, as I said, we dropped subscript B, otherwise R dot is VB. So, and at the end we used coordinate transformation to compute velocity upon B. Now, the second step is we are interested in computing acceleration for point B. Just to remind you, acceleration was R double dot equal to R circle 2 omega cross R circle plus omega dot cross R plus omega cross R. Now what we need to do is to go through this equation term by term and determine each term. So let's just start with this term, R circle. What does this term represent? If you think about it, we said that this R circle is the acceleration in body attached frame. So now, how do we compute R circle? Again, if I think myself as the observer and attach myself to body attached frame, this frame, and I watch point B, what do I see? I see that point B, the distance, because I'm at the origin, I see that the distance of point B with respect to myself at the origin is increasing at a constant rate, which is 2.25 meters per second. And because it's a constant rate, I do not see or feel any acceleration. So to me, as somebody who is attached to body attached frame, the acceleration of point B is 0. So to me, this term is equal to 0. All right. Now let's just skip the second term and look at the third term. Omega was angular velocity vector for body attached frame. And we said that the body attached frame, or the body itself, rotates at constant angular velocity. So angular acceleration is going to be 0. Omega dot is going to be equal to 0. So this term is also equal to 0. So we end up with these two terms. Now the good thing is, if you look at these two terms, we have already talked about omega and R circle, right? Because omega was the vector omega in equation 2, describing the angular velocity of body attached frame, omega 2 about j hat and omega 3 about k hat. And R circle was equation 4. We have already computed R circle, and R was equation 3. So what we're going to do again is use equations 2, 3, and 4, and let's call this equation 5 in 5, and this is what we get. If we do that, we get omega, let's do it, omega cross circle. So all we need to do now is, because we have already computed those terms, we need to compute only the cross product. So the cross product, so you can do cross product different ways. One of the various ways I discussed in class, and one of my video lectures, was you can describe this cross product in matrix form. And if you do that, so this time I'm going to do it this way, so you also practice this way. In using matrix or matrices, we said that this is our omega. If you go back 4 lectures back, we have minus omega 3, omega 2, omega 3, and omega 2, 0, 0, 0, 0. Why do we have these two equal to 0? Because omega 1 is equal to 0. And then we multiply that by our R circle. So our circle was 2, 1, 6, 5. 0.125 and 0. Again, to remind you, our circle was here. If you look at our circle, your first component is 0.2165, and the second component 0.125, and third component, k hat component, is equal to 0. Right? So if you compute this, you get 0.05, 0.0866, and negative 0.065. All right, so we have computed we have already computed omega cross, so we simply need to multiply it by 2 to compute 2 omega cross our circle. The other term we have is, let's call this 6, is the last term. So I have omega cross R. Again, to remind you, it matters where you place your curly brackets. You cannot cross product omega by omega and then by R. So what do we have here? All right. So I'm going to also use this omega cross R I had before, because if you recall, we have done omega cross R here for velocity. So I'm going to use that. So again, this is omega. This is my omega, and then this term in bracket was equal to what? If you recall, I had done this omega cross R before. So, or if you don't recall that, let me just remind you, omega cross R, you can do this first, and this is equal to negative 1.2 I hat plus 2.078 j hat minus 1.559 k hat. Right? So I'm going to use this omega cross R here, 2.078 and negative 1.559. Right? This is simply a matrix product. A 3 by 3 matrix multiplying a 3 by 1 vector, it gives you a 3 by 1 vector. All right, and this is equation 7. Right. And then at the end, we're going to use 6 and 7 in 5. So what we are going to get is R double dot being equal to, and then I'm going to also simplify the terms and just write the final answer here. It's pretty straightforward, I guess. And if you have any question, you can always email me. Minus 1.4 I hat minus 307 j hat plus 0.23 k hat. And this is meters per second squared. And again, to remind you, our double dot was our acceleration. Again, let me just recap what we had. So we started by computing velocity. We used two frames. We used a body attached frame and an initial frame. So we described the motion in our body attached frame, and then we used coordinate transformation to compute the unit vectors of body attached frame in our initial frame. Let me just move this so that it's clear what I did. So, and then once I have this coordinate transformation, so I can compute velocity for point B. Right? And then once I have velocity, I can also compute acceleration of point B. Again, same thing. So we have already computed all the parameters in body attached frame, and then we used coordinate transformation, then we computed velocity, and then we're computing acceleration. Again, let me just remind you. So once you write down, let me just go back to our velocity again. So in velocity, so you start with this equation just like acceleration, right? So initially, because that's one of the advantages of using a secondary body attached frame, initially you compute omega, or you describe R and R circle in body attached frame. That's why we had B1 hat in for R circle and R. And once you have these two terms, or these two expressions for R and R circle, then all you need to do is to do a coordinate transformation, right? Because at the end, when we want to add R circle to omega cross R, we want to have everything in one frame. So we want to have everything in one frame. So now that I said that, think about this. What if I describe everything in body attached frame? Because I could have done that, right? I could have kept R circle and R in this form, and then in equation 2 have used reverse transformation and described J hat and K hat in body attached frame. Right? So what do you think the difference is going to be? So think about that, because if I don't specify at the end, if I don't specify the frame, you could use any frame. As a matter of fact, once you're, for example, for velocity, once you're at this point, you could say, you know what, I want to define a polar frame now, or this is a three-dimensional motion, a cylindrical frame, and define my motion in that frame. So I want you to understand the independence of the frame in which you represent your results. You represent your results, and the difference between that and the difference and the frame you're computing all your results. In other words, for your computations, you should have all your terms in one frame. Otherwise, here you would, when you're adding the two vectors together, you're going to have B1 hat and I hat, B1 hat, B2 hat, B3 hat, and I hat, J hat, and K hat. So you cannot simplify that. You need to first describe B hats in terms of I, J, K, and then add or subtract terms from each other. Thanks for paying attention. This was today's lecture.